I was watching YouTube the other day and I came across this new product called Levy Floating Plant that featured a levitating plant pot that rotates. I was instantly curious, how did they do that? And it led me to the different types of levitation, and I thought I'd show you the super interesting concept of quantum levitation. Levitation is a process in which properties of quantum physics and electromagnetic fields interact to create a levitating effect. To this better, we must understand electrical resistivity and electrical conductivity and how that applies to magnetic properties. Electrical resistivity is a fundamental property of a material that quantifies how strongly it resists electric current, like a hose with sand in it. The higher the resistance, the lower the power of the current flow. Materials like rubber, paper, glass, and plastic, for example, present high resistance to electric currents. Electrical conductivity quantifies how strongly electric currents can pass through the material. Materials like silver, copper, gold, and aluminum, for example, make very good conductors. The next thing we need to understand is the relationship between magnetic and electric fields. The magnitude of the magnetic field is directly proportional to the current circulating in the loop. Both fields are interrelated and known as the electromagnetic fields. Currents can pass through and resist charges, so can the magnetic field. Magnetic flux is defined as the number of magnetic field lines passing through a given closed surface. Now that we have some background, let's get into the good stuff. The properties of quantum physics used in quantum levitation is called a superconductor. A superconductor is an element or metallic alloy that can be cooled down below a certain critical temperature, usually close to absolute zero, to lose close to all electrical resistance. This allows superconductors access to supercurrents, where the electromagnetic current flows without any energy loss. This isn't the only superpower of superconductors. The lack of resistance in superconductors creates this phenomenon when paired with the magnetic field called the magnetic locking effect, which allows the superconductor to achieve this levitating effect. But what allows this to happen? The Meissner effect, the expulsion of magnetic field from the interior of a material, meaning when a material is in the process of transitioning to a superconductor, it starts to lose its resistance to all electromagnetic currents, which allows the material, when exposed to a field, to prevent most magnetic fields from entering. So the magnetic field ends up going around the material and creating a pocket in the magnetic field. There's been known to be two types of conductors. For type 1 superconductors, only the Meissner effect occurs. However, if only a Meissner effect was occurring, that wouldn't achieve this locking effect. It would only try to run away as fast as it can from the magnetic field. That's where type 2 superconductors come in. For the type 2 superconductor to achieve this levitation or locking, some part of it still needs to be attracted to the magnetic field. This is why type 2 superconductors intentionally include impurities to allow some of the magnetic field to bunch up and pass through the material. This is called flux tubes. The superconductor is then locked in place because it would require energy to alter the position of the flux tubes, and the superconductors can't lose their energy, so they naturally want to stay locked in place. Type 1 superconductors are well known for their use in transportation, like levitating magnetic propelled trains developed by the Central Japan Railway Company. Type 2 superconductor applications are less developed, but as technology evolves and discoveries lead to higher critical temperature values, something like flying cars might be possible in the future. That was a lot, but that was mind-blowing. Thank you for learning with me.